So let's talk about resistance. I want to tell you guys like what resistance is. Like, what is it anyway? I mean, you have a good understanding of what resistance is. It's something that resists something, okay? So yeah, if you're trying to, go somewhere and like there are all these things stopping you from going there, they're resisting you from going there. So when we talk about resistance in electrical circuits, we're talking about G. Yeah, let me just point that out. You like my new pointer? It's like, oh, where'd it go? It's purple now. There's a G. Yeah, because that's for resistance, right? Yeah, no. G is actually for like the opposite of resistance or the inverse of resistance. Something that I think you have to get into and have a better understanding of to understand what resistance is. So in electrical circuits, when we're talking about resistance, we're talking about the resistance of flow. And ultimately, if you want to like boil it down to kind of like a tangible kind of picture, you can watch the electrons flowing through the wire. And there's some element in the wire, there's some nature of the wire itself that changes so that the current doesn't flow well through it, or those electrons can't flow well through it. I think before we move forward, I have to stop and pause for a second. What's pushing them? Yeah, it's the voltage. Okay, so we understand, from the video that you watched in this series, this part 1 video, you've really got a good handle on the nature of voltage. And the nature of voltage is there's this energy that's pushing charge. And I'm going to boil charge down to electrons. So I want you to envision just an electron, okay, or just a bunch of electrons going through a wire. Let's call it a copper wire because copper is really conductive. Oh, there's that word, conductance. Maybe that's important. Yeah. So the wire is really conductive because it's copper. The electrons can jump between electrons, between atoms really easily. And they're jumping because something's pushing them, and there's that energy that's coming from the power source. We call it electromotive force. Actually, voltage and electromotive force are the same thing, or EMF. But let's just say it's electrochemical energy that's actually coming out of a battery, and that's actually pushing those electrons, and we call that voltage. But the voltage specifically is about how much current is applied to the number of electrons. But let's just look at it called like a pressure or a push. So here we go. So there's the electrons, and they're getting pushed through this wire. You can envision them like a tube going through the wire, or the electrons going through a tube or a wire. Now, what's going to happen is that they're going to come across a spot in the wire, or maybe the wire is actually connected to some other thing, where that other thing, for some reason, restricts the flow. So the electrons do not travel as easily through that. Now, it could be the wire is connected to something that's no longer copper. So the electrons have to like leave the copper and then go into another thing. And maybe that thing has less conductance. Yeah, it doesn't conduct as well. So it resists the flow. Actually, it could be that thing is actually another thing that's designed specifically to steal some of that energy and use it. So what's going on is that energy that's pushing those electrons, the electrons go through there. The electrons, they don't slow down in their speed, but the flow rate of the electrons decreases. And of course, we call that current. So the flow rate decreases, and then there's some energy lost. And this really ties back to voltage in a big way, because that energy that's inside the voltage is actually being gobbled up by the thing that has a resistive nature. It's being gobbled up, and then it's actually used for something. It could be used just to create heat. Now, generally, most resistors, things that have resistance and very defined resistance called a resistor, which you guys know what resistors are, and you can imagine them, and I'm not even going to show you a picture of one because you know what they look like. Those resistors, they're designed specifically to apply a certain amount of resistance to that flow. But if resistance is just kind of stealing energy, what happens to the energy? Yeah, it turns into heat. So resistors, essentially, their whole shtick is to take the energy and just turn it into heat. Just go make some heat, and it slows the current down. So we're kind of trading that off. It's almost like this thing is doing some work. It is actually. Well, think about it. Work is energy over time. That's how we define work, right? So the use of energy over time. So the electron is actually making work happen. Does that make sense? Yeah. So without resistance, we can't make work happen. We can't do work. It can't happen. So, I mean, if you're going to push a rock up a hill, okay, there's resistance involved because, gravity and the rock is heavy and there's a friction and all the rest of it. Well, you're doing work, but, without that rock giving you resistance, there's no work done. right? So there's no force. There's no counter force to that push. So in the same way, there's this energy pushing these electrons through the wire, and they come across some other thing where the conductance is low. Now the conductance in resistors is actually really low, and that's why we say that they have resistance, because obviously from this slide they're inversely proportional. And yes, G is for conductance, which is kind of a weird symbol, but just deal with it. So the conductance is gets lower in a resistor, and then obviously it slows down the current and it steals some of the energy, makes heat. Are there other things that have resistance that don't just produce heat? Yeah, how about a speaker? Makes sound. I mean, sound is measured in decibels, and there's a certain amount of energy. Actually, speakers are measured in watts. Oh, no way. Watt is the use of energy. No way. Speakers have resistance, and they're stealing the energy, and they're making sound, and that's why they're rated for a certain power. Oh, that's cool. Yeah, because they're taking energy. Okay, so resistance, speakers have resistance for sure. Actually, you may know a resistance number for speakers. It's either 8 ohms or it could be 4 ohms. Depending on, there are other kind of things about that speaker that define how much energy it steals. More specifically, how much current you put through it, which is all linked to power, but I'm not going to go there. That is another device that has resistance. What about something else that we put current through, we apply that energy to, those electrons, that we're pushing them through this thing, and they steal energy and they slow down the current? How about a solenoid? Yeah, an electric solenoid, it's pushing and pulling and pushing. It's creating this magnetic field, and it's maybe pushing something or pulling something, and it's actually applying a force. Oh yeah, like force is in here as well, because we were talking about pushing that rock up that hill. So there you go. So I've got a device that creates a force, and that force is being used in application, and it's doing some work. Hey, there's that thing with work again. So resistors are devices that actually transfer the energy coming from the power source, from the voltage, whether that's a battery or some other kind of generator, and it transfers that energy into some form of work. Sometimes it's just creating heat. Now, the other thing is, obviously, I think you kind of going there in your head, is an electric motor. So cool. So those are all the devices. Now, what I want to do is I want to talk about a little bit more theory about like the math and some of the terminology that we use for resistance, and then that's it. I mean, this was me just talking to you about the nature of resistance. It doesn't get that much more complicated. Like I said, there's some formulas, which actually we can see on the screen here. The other thing is I just want to jump over to Blackboard and show you another really cool video that is about the nature of resistance. I go into a little deeper about resistance, but that goes beyond the nature of this course. If you don't watch that video, you're not going to lose any knowledge, and you're still going to like get 100% in this course, no problem. But it's a pretty cool video. So here I am just jumping over to Blackboard, and we can see that there's this video on voltage and then the video on current, which really sucks. Sorry about this video, it totally sucks. I did that on my mother's back porch, but whatever, deal with it. It still has the information in it. And there's this video here that we're watching now. And then there's this really cool video down here. And it's just, it's me in my lab actually putting resistance, kind of testing out resistance, like seeing how resistance, current, and energy and stuff work and what's actually going on. And there's actually a motor in there. This really cool thing about that video is that because we know that resistance and power and energy and current are all kind of linked, if a motor does more work, well then it's stealing more energy, so therefore it must be changing its resistance. Really? Yeah, cool. Some things change their resistance. And not only that, actually, there's some other things that specifically are designed so that we can vary their resistance. And yeah, there's a lot of really cool reasons why we may want to vary the resistance of a particular thing. So starting from this just first slide in this PowerPoint here, we can see that the property of a material to resist current is actually the resistance. It's actually the opposition to current. And where the current through any material has resistance, heat is produced by the collisions of the electrons in the atoms. Yeah, there's actually like kind of friction going on, and there's heat produced. But like I said, resistance doesn't just transfer energy into heat. It does other things. But because of the second law of thermodynamics, which we don't have to go into, however you look at it, whichever device you are using that has resistance to actually do work with, it's also going to produce some heat. So that's kind of something you have to keep in mind. So now we're just going to go into ohm, the resistance unit. Make sure you always put units in all of your formulations. Even if you have a formula where there's resistance over resistance and you know the ohms just cancel out, put the ohms in. You have to be accurate in your presentation of your documentation. Good. So the ohm exists if there's 1 ampere. So there's actually some kind of definition of 1 ohm. Yeah, an ohm is a value of measure. It's what we measure in. So therefore, there must be some kind of definition of, how to know how much it is. And it's this. 1 ohm of resistance exists if there's 1 ampere of current in a material when 1 volt is applied across that material. So we know that voltage is really linked with energy and current and energy and coulombs or charge per se. So if I were to push 1 amp, so that's actually a flow rate, a coulomb per second. So if 1 coulomb goes through a particular material in 1 second, and if it requires 1 volt, then 1 volt if it loses 1 volt, which is really linked to how much energy is lost, and therefore power, because losing energy at a particular rate. So that's actually 1 volt, which is a joule per coulomb, which is pretty cool. So if you lose 1 joule of energy pushing 1 coulomb through some material, and that takes 1 second. So if it takes you 1 second to push 1 coulomb of material, 1 coulomb of charge, through a material, and it takes 1 second to do so, that's an ohm. I mean, yeah, you can sit with that a little longer. This actual sentence here, 1 ohm of resistance exists if there's 1 ampere of current in a material when 1 volt is applied across the material, kind of ties it down kind of accurately. But you can think about the physics of that in that last sentence that I just said and sit with that for a bit. But if anything, the best thing to do is just kind of move forward and actually use ohms and use them in calculations, and we'll just see how that goes. I didn't say that right. I want to say that again. Imagine this. I have some material that I want to shove some charge through. I've only got 1 joule, okay? If I use 1 joule to push that charge through that material, and if I could do that with 1 joule and get it through that material in 1 second, then actually that material has a resistance of 1 ohm. So you get that? I got this material. I've only got 1 joule of energy, and I've got 1 coulomb. Okay, you know how many that resistance, you know how many electrons that is, right? So I got all these electrons. I want to shove them through this material. I've only got 1 coulomb. If I do that, and I get them through, and that happens in 1 second, the nature of that is 1 ohm. If it takes 2 seconds, it's actually 2 ohms. That's pretty cool. So the symbol for ohm is omega, and it's that ohm symbol, and we know that, and that's cool. So I did say conductance is a big part of this. So let's just talk about conductors, something that's conductive, right? So it actually has to do with what's going on inside the material, what those materials are made up of, and ultimately it boils down to how many valence electrons are actually around the atoms that are making up that material. Boiling it down with our valence electrons, if it's got 1 valence electron, well then that's actually really good, because you can kick that valence electron, jumps around really easily like copper, right? And actually if you've got 2 or maybe even 3, it's pretty easy to kind of kick them off and move them around, and they'll actually flow through the material. Obviously 1 valence electron will jump around easier than say 2 or 3, but if they're 1, 2, or 3, we call that a conductor. It has the ability to conduct. If it's got 3 electrons, it's not quite as good as conducting as something with 1 electron in the valence shell, but it's still, we call it a conductor. Then there are things called semiconductors, and I think you guys know this, but if you had 8 electrons in the valence shell, it's really happy. I mean, it doesn't want to lose any electrons, and those are actually called insulators, or they're things that actually, don't allow current to flow at all, or more specifically, they have a very high resistance. So in that middle is something called a semiconductor, and you've heard that term before, and certainly we'll get into that in another course. But for now, just remember they have 4 valence electrons. They're not really very good at conducting, although they do conduct. They're kind of in the middle. We don't use them if we want to conduct a lot. There are reasons maybe we would want to use a semiconductor. We won't get into that. I just need you to understand the terminology here, and more specifically in the application to say, why do electrons flow through something easily and or not easily? Well, because of the nature of the conductance of that material. Now, we did see from that first slide, the conductance and resistance are completely inversely proportional. So if the conductance is really high, then there's really low resistance. If the conductance is ridiculously low, there's very high resistance. For instance, this is crazy, but I'll just do this right now. What's the conductance between the metal in this pen and these scissors? Well, it's ridiculously low because essentially there's a big gap of air in between. What's the resistance of that gap of air? Does it have resistance even? Yeah, it does. We could actually measure the resistance of this air. If I wanted to, I could just take 2 probes and stick them together and say, hey, what's the resistance between these two? And it would be ridiculously high. But the air actually has a resistance in that it has a conductance. It's extraordinarily low. But electrons can fly through the air. You've seen that happen in sparks and stuff. So the air actually has really, really, really high resistance and a really, really low conductance. But you've seen electrons and sparks jumping through things, and arcs, or even lightning, right? It actually jumps through the water and other minerals and stuff and other particulates that are in the air. They help the conductance. But it's terrible conductance, but its resistance is really, really, really high. So if I just had a copper wire, I don't have a copper wire, but if I just had these, okay, let's go back to the 2 pieces of metal, and I just connect them together. Now, this is made of steel, right? These are my grandfather's scissors. These are like super, super old, and they're really cool, but they're made of steel. I don't know what kind of steel they are, and this pen has got some steel on it as well. If I touch these things together, what's the resistance between these? Probably really, really, really low. The conductance is really high. Or even just specifically, what if I stuck a probe on this side of these scissors and a probe on this side of these scissors, and I measured the resistance? Well, I could easily find the conductance by finding the inverse of that. But let me just take something else here. Even this pen here, I don't know what kind of material this is. Let me just grab something else here that has a different conductance. Okay, I've got some things here. I've got some copper wire. This wire is made of copper. This wire is speaker wire, and I'm not sure why they made this speaker wire out of aluminum, but this is aluminum speaker wire, okay? So its conductance is not as good. And although it does conduct quite well, but it has more resistance than this does. Does this copper wire have resistance? Darn right it does. It has resistance. So actually, that's one thing we have to keep in mind when we're designing our circuits. When we're actually putting wires in, we have to think of that conductance, or more specifically, how much current we can put through them, and if that current is going to generate heat, or if the material itself is going to have a resistive nature, it's going to steal some of that energy as a resistor in the circuit because it has resistance. So there you go. There's conductance and there's resistance, and you guys understand that it has to do with the valence shells. And let's move on to just this formula here, which is really simple, and we can just say they're directly inversely proportional, no problem. And I think the only thing we can get out of this slide that we don't know so far is that the unit for conductance is a Siemens, and it's a capital S, not a lowercase, because a lowercase s is for something else. Yeah, seconds. Let's move on. I did mention we had these adjustable resistors. They're called potentiometers. I have 2 pots here as an example. One's called a trimming pot. It's a tiny little potentiometer. And then the other is just a potentiometer or a basic pot. And you can see they all have 3 pins on them. And what's going on there is that you've got one pin that is kind of one side and one pin is the other. The 2 outside pins, they have a total resistance. Now the inside of the potentiometer has this thing called a wiper on it, and it touches onto that strip. It's called a resistive strip inside. We don't need to study that right now. Right now we're just talking about what the nature of resistance is. In the labs, you'll be able to study, how to use pots and how they work. But for now, I just want to say, generally there are 2 kinds of pots. One is a trimming pot, which is used to kind of put into a circuit to actually trim or just kind of have that circuit and just kind of tune the circuit a little bit. And again, as far as like tuning circuits goes, we'll get into that way later. And right now, we just know that we have two different kinds of pots, and they're essentially variable resistors. And there are lots of reasons why we may want to vary the resistance of something. One of them is actually to steal energy from the circuit. Yeah, if you want to increase the resistance, you're going to steal energy from the circuit, and then from there, actually, there's less energy for things down the line. And like maybe a light bulb. Maybe you want to control how bright a light bulb is. You can do that with a potentiometer. You can also use a potentiometer to control things. Yeah, not just to control the speed of a fan, which is actually, in many cases, a potentiometer is used to control the speed of the fan by just stealing energy from it. Or the other thing that we can do with these things is we can tune how much voltage something gets in a control system, like volume. I mean, there's not a lot of current or anything going through your volume switch. It actually just kind of tells the amplifier, hey, by the way, do this, this is how much you should do something. It's a control aspect. Also, timers. Timers are really cool. Timers use variable resistors called potentiometers. So really cool. So they can be used as voltage dividers or current dividers. Yeah, pretty cool. And there are different names for these things. One is called a rheostat, and the other is called a voltage divider. And we'll see that when we get into lecture later on, when we're actually studying voltage, current, and Ohm's law. You put them all together in a circuit. Here we go. Just different kinds of pots. You can see all of these are kind of labeled and piled up on each other. Lots of different kinds. These are the different kinds of trimming pots. And essentially, this is a linear trimming pot. And then some trimming pots are really super crazy sensitive. Like you have to turn it like 15 or 20 times to make the wiper go all the way from one side to the other. And some you just turn, almost all the way, almost 360 degrees. Lots of different kinds. This one, you turn maybe 270 degrees or maybe 365 degrees. This one you turn many, many, many times as this slider goes back and forth. And this one's geared. This is a really sensitive one. This one you could turn it 2 or 3 times and the wiper would barely move. So if you want to control the resistance really accurately, you use one of these guys. Really cool. And these you will see in amplifiers. If you ever pull a radio apart, you'll be able to see these guys in here. And any controller that has to control more than one thing at the same time, you're going to have these kind of multiple pots. So there's just a shaft in there, and it's controlling all the wipers. So we have all these different kinds of pots. And then inside, this is the concept of where the wiper is. This is the resistive strip inside, and that's the wiper. So if I were to, say, put some kind of meter on here, like a DMM, a digital multimeter, and measure the resistance from 1 to 2, and it would say 1,000 ohms. If I were to move this wiper over here, and let's say I moved it 1/3, if I studied the resistance between port 3, and you can see port 3's got a little wire going there. If I studied the resistance between port 3 and port 2, it would be 1/3 of 1,000 ohms, so 330 ohms or so. If I were to study the resistance from here to here, it would be 370 ohms or so, if it was about 3/4 of the way of turned. So as I move this, the resistance between either 1 and 2 or 3 and 2 change. And as you can see, if I were to study the resistance between 1 and 2, and I were to turn it, say, clockwise, the resistance, depending on which way you look at clockwise, the resistance would either increase or decrease. But if I studied the resistance between 3 or 2, the resistance would do the opposite. It would either do clockwise or counterclockwise, but it would be the opposite of whichever I was measuring from 1 to 2. So depending on which way you connect this, you can either make the resistance increase as you rotate it clockwise or decrease as you rotate it clockwise. There are kind of 2 ways that we can hook these ports up. One is just as a voltage divider, and we just kind of call that a potentiometer. And the other is a rheostat. Now, I'll just go in the voltage divider for a sec, and then we'll delve into the rheostat a little bit more. As far as the voltage divider goes, if I were to put voltage on one side and, say, ground on the other, and if I were to tap into 3 and move that up and down, I would actually see a different voltage coming out of 3. So it's actually pretty cool. It's actually a voltage controller, or we call it a voltage divider. Again, if I were to, say, put the positive of the battery here and put the negative of the battery here, if I were to study the voltage coming out of here relative to, say, port 2, if it was connected to ground, and if I were to turn this wiper, I'd actually get a different voltage coming out. It's pretty cool. Again, we'll study that in the labs a little bit more. This is a rheostat. It's called a current divider. This is the symbol for a rheostat. This is how a rheostat is connected. Again, we will look at that as well. So the only thing I want to do is just before we kind of let you go here and talk about a control discussion and then let you go, is I just want to say that we have two different kinds of these variable resistors called potentiometers. One is logarithmic, and the other is linear. We're going to use linear in control systems much more. We're going to dim lights, motor speed, and a lot of other things, position controlling and time settings for sure. You will see logarithmic potentiometers as that if you turn, you can see these are the degrees of rotation. As I turn the different degrees of rotation, you're going to get a different resistance. And you're going to see that's a logarithmic value. And that value is used, this type of potentiometer is used for audio controls, big time. So in control systems, we're definitely going to be using linear pots, and they're going to look like this. Now, as far as application goes, there are a lot of really cool things, and you can see that essentially we've got two different kinds of things here. In this situation, we've got a voltage divider. We've also got a voltage divider over here. In this case, as I'm moving my wiper, I'm controlling the brightness of a lamp. As I'm moving my wiper here, I'm controlling the strength of this speaker or this kind of siren or buzzer. Over here, this is what's going on called a rheostat. I'm controlling the speed of the motor with a rheostat. Now, generally we don't control things with pots directly that are drawing a lot of current. Maybe this motor is maybe a 1/2 amp motor. Anything more than that, and I'm going to need to have another kind of way to control this, especially if this lamp is really high, a lot of current going through there, like a 100-watt lamp. I might not use a pot to do that directly. There'd be more of a complicated circuit. Again, we use these things, we use voltage dividers and potentiometers to control loads that don't actually have really low resistance. And you'll see in Ohm's law what I'm talking about. Let me just pause on that a second. They don't steal a lot of energy. If they're stealing a lot of energy, the pots actually get hot because they're resistors themselves, so they're going to be stealing energy too. So if you've got a lot of current flowing through here, like really high value of current, there's actually going to have to be a lot of energy that's produced or energy that's released and power that's actually being done. So essentially, if we have low power devices in that they have high resistance, yeah, that's really weird. A high resistance is a low power, and a low resistance is a high power. The reason low resistance is high power is if there's a really low resistance motor, it's not resisting current, so there's a lot of current going through, which means actually a lot of power. So with that said and done, I don't want to go into anything more deeper than this. We've talked about this. I'm just going to, before I leave this slide, I'm just going to say we can use potentiometers, variable resistors, as voltage dividers or current dividers, and we're using them to control loads that do not demand a lot of current, just low current loads. But control is all about what we're doing with potentiometers. That's all I really wanted to unpack with you guys as far as resistance goes. So we know that resistance and conductance are so linked together, but they're inversely proportional. We know that ultimately a resistor is a device that's going to steal energy from the voltage and do work with it. Depending if it has really low resistance, it's actually going to be doing more work. That's weird. But if it resists the flow less, there's going to be more flow, so therefore there's more work done. And if it resists the flow a lot, if it's got really high resistance, then actually not a lot of work is going to be done because not a lot of current is going through. So if you want more current to go through the same resistor, you have to put more energy into it. And to do that, then you're actually going to be burning more energy. So what I just said there kind of confuses things a little bit. You may not get that unless you understand Ohm's law. What I'm just going to leave you with is that resistors resist the flow, and conductors allow things to conduct, and obviously they're inversely proportional. That's it. Oh, goodbye.